Welcome to Museum of the Rockies in Bozeman, Montana. We are so excited that you're here for today's program with streamable learning on the rock cycle. My name is Angie. I'll be your host for today's program. I'd like to introduce you to our paleontologist, Amy. Amy is going to be sharing the rock cycle with us today. Before we get started, a couple quick things to note. We will use the chat box throughout the presentation. Go ahead and jump into that chat box if you haven't already. Let us know where you're tuning in from and what grade you're in. We are excited you're all here. You can use that chat box to ask Amy questions also throughout the presentation. The other thing I want to share with you, this program is about 35 minutes long. So we will ask questions throughout. We'll try to get to some of your questions at the end. But Amy, we're ready for the rock cycle. Thanks so much for joining us today.
Yay! Thank you so much for having me, Angie. And thank you all for joining us today. A little bit about Museum of the Rockies, where we are located. We are in Bozeman, Montana, in southwest, beautiful Bozeman, Montana. We are, if you check us out on the map, we are located just a little bit north of Yellowstone National Park and about 100 miles south of the Canadian border. Here's Big Mike. I think this picture was taken today. We got a lot of snow last night and this morning. So Big Mike is a bronze T-Rex that greets visitors who are visiting Museum of the Rockies. Hopefully some of you have had a chance to see Big Mike in person. If not, come visit us sometime. Now this is one of the only dinosaurs we're going to be talking about today, as today's topic is the rock cycle. So the rock cycle is a concept that we use to explain how the three main different types of rocks on Earth are all related to each other. And how that they can actually turn into one part or another. So here you can see the three main types of rocks on your screen are sedimentary, metamorphic, and igneous rocks. And you can see, and we'll be talking about today, how all of these rock types can actually turn into the other through different processes and over long, long periods of geologic time. Thank you for that. And I think we're going to go into our hand samples here. So again, we're going to be talking about igneous, sedimentary, and metamorphic rocks today. And we're going to be talking about how they're all related to each other. We're going to be talking about where these rocks are formed in terms of the earth and the surface. And we're also going to be talking about the processes that help these rocks form through pressure and heat, plate tectonics, and erosion. And we're going to really just talk about how much geology rocks today. Lots of bad jokes. So let's start out with igneous rocks. So we're going to, our little pointer there. Igneous rocks is really just a fancy term for volcanic rocks. Rocks that have originated in lava or in magma or in actual volcanic explosions as well. So igneous rocks are formed usually at depth, so beneath the Earth's surface, and a lot of times they're forming in melting scenarios that causes magma to form underneath the Earth's surface. And as these rocks are either cooled underground or as they're being extruded through a volcano, they cool and crystallize. And those ingredients, this melted rock that cools and crystallizes over time, is really the important ingredients to all igneous rocks. Now, we also have two types of igneous rocks. We have got intrusive igneous rocks, and we've got extrusive igneous rocks. And again, those are fancy words that essentially mean forms inside the volcano igneous rock, or extrusive, X, outside of the volcano igneous rock. So let's talk about the ones that are forming inside. And let's see. As this magma, so we've got molten rock, right? That's magma. We've got that underground, and we can tell that it is this rock cooled underground and not as it was coming out of the volcano because of its crystals. All right, you can actually see visible crystals because it had time to cool slowly and form. Versus if you have an extrusive rock, it came out of the volcano and it cooled so quickly that crystals didn't form at all. So the way I remember this is I actually think about when I am rushing to get out of bed some mornings, or maybe you when you're rushing to go to school. And if you have no time and you overslept and you got to jump out of bed really quick and you don't have time to make your bed or brush your teeth or comb your hair or even get a nice outfit on, and you're just kind of all a mess. Well, that's kind of like how extrusive igneous rocks form, that they have to crystallize really, really quickly because they are exposed to the Earth's atmosphere and it cools so quickly. Whereas these intrusive igneous rocks, now that's more like on a Saturday morning when you have time to just stretch out and like fully form and get yourself all nice and put together and looking real good. That's kind of what I think of as the intrusive internal igneous rocks that have enough time to slowly cool and crystallize and actually see these different big crystals within the rocks. These big pink ones are potassium feldspars. And that is a good indication that you have a granite. This is a type of granite. You might have a granite countertop at home. And if you do, try to see if you can find any big crystals like this, or even smaller crystals like the darker ones and the lighter ones there too. Granites are, this type of granite is, see, eroding right in front of us. The rock cycle is happening. These ones are really fun for rock climbing too. If you ever get a chance, try doing some rock climbing. Now, those granites tend to form inside a volcano, or in that's a melted rock that cools internally versus coming out. Now, that means magma that never makes it outside of the volcano can cool and turn into something like a granite. Now, I want to ask you, what's the difference between magma and lava, and how does it pertain to what we're talking about right now? So go ahead and type away in the chat box there. Let us know if you have an idea of the difference between magma and lava. And we're going to talk more about lava here in just a moment. As you type those in, I'm going to show you a type of extrusive igneous rock. This is called obsidian. It's very, very black and dark. And it has no crystals forming at all because it is shot out of the volcano so fast that it actually is a version of volcanic glass. And that's why you can see all of those curved, broken surfaces that looks like maybe a bit of broken glass. Those are, it is volcanic glass, which is really, really cool.
We've got lots of good answers coming in. Magma's under the ground, lava's above.
Magma under, lava above. Yes, yes. Sounds like you all had it. You know your stuff. Hopefully some of you have had a chance to see cool lava in person, maybe in Hawaii somewhere, but that's exactly right. So the magma that is cooling underground is going to turn into granites, and the magma that actually is extruded out of the volcano is what we call lava. So this is an example of lava. This is basalt, which is a type of lava. And this type of basalt is called pahoehoe lava because it is ropey and smooth in general texture. And this is an indication that it came from, yes, a volcano eruption, but not a really explosive one. It indicates that it came out of a volcano where it was more like blub, 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 like what we see in Hawaii in a shield volcano. And it didn't have big explosions that were knocking down forests and making people evacuate from their towns. No, this is a more slow moving lava, and that's why it gets this ropey texture here. And it has a lot of iron and magnesium in it, which is what gives it this darker color. Now, we do have volcanic rocks that are from more of a big explosion. So this is a chunk of rock called an andesite. And now andesite rocks are volcanic rocks that come out of a volcano that actually have a lot more silica in them, more so than iron, which is why it's not quite as dark in color as that other lava. And you, again, cannot really see individual crystals. You can see some different colors, but not fully formed different crystals because it didn't have enough time to fully form those as it came shooting out of the volcano, kind of like Mount St. Helens or Pinatubo or some other large volcanic eruptions that actually take out a lot of a more violent eruption, if you will.
Interesting. Someone said they live in Montana, so no volcanoes.
Ah, yes. So volcanoes in Montana, we do technically have volcanoes. They're not necessarily as active as some of the ones that we have on the West Coast, but the ones that were outside of Yellowstone National Park were all erupting about 55 million years ago. And just because that they aren't erupting currently does not mean that they will never erupt again. That's the beauty of the rock cycle. Things are always changing, but on a very, very slow scale. Very hard for us with our human lifespans to be able to actually quantify geologic time and how long it might take before the Absorca volcanoes are active again necessarily. But great question, or great observation with all of that. So the last thing I want to mention about our cool igneous rocks is that sometimes the magma or the lava can have open cavities within it, or fissures, that are slowly filled in over time through hot mineral-rich water that precipitate out or form beautiful crystals like this big, beautiful amethyst crystal that formed within a volcanic rock. So not only can we talk about really, really cool rocks, but we are also talking about cool minerals and where they form and where you can find them as well. Also, that one is very heavy. All right, our next rock type that we're going to be discussing is sedimentary rocks. All right, sedimentary rocks are my favorite. I am biased. I am a paleontologist. And where do we find fossils? We find fossils in sedimentary rocks. So these fossils up here, though these are actually replicas, they were found in different types of sedimentary rocks that we're going to be talking about today. So igneous rocks, we just discussed, are forming underneath in Earth's internal heat or as it's being exploded out of a volcano. Sedimentary rocks are actually forming on the surface of the planet, and they preserve past surfaces as well, like a sand dune or the banks of a river can be preserved very well in sedimentary rocks. Sedimentary rocks, as it sounds like, are made up of sediments. So sediments are bits of broken down other rocks. And so that can oftentimes be igneous rocks, metamorphic rocks that are breaking down and eroding and breaking into tiny little grains that are then re-cemented into sedimentary rocks. So those kind of sediments are going to be things like clay and silt and sand and cobbles and weird limey mud and things like that nature. And a lot of times these rocks start off as sediments that are then carried in rivers and deposited in rivers and lakes and oceans and estuaries and deltas and water-rich environments, because the water has to be transporting them. So these dinosaurs probably died along the banks of a river or nearby a river that flooded, and those sediments over millions of years covered up those dinosaurs and preserved them to be found by us 66 million years later, which is so cool. Okay, so our first example that we're going to talk about of a sedimentary rock is this one right here. So this is sandstone. I bet you can guess what sandstone is made out of. It's in the name. So sandstone is made up exactly like you think of sand grains. A lot of times we get sand that is forming in a river environment or an ocean or maybe even a sand dune at the beach. And as the layers, see how you can see layers of rock in here? Those are all different depositional times. So maybe a flood came through and laid down one layer, and then another flood came through a little bit later. And as they accumulate, they bury the sediments. Those sediments essentially bake a little bit underground and are cemented together to no longer be a loose sand dune, but is actually now a solid rock. That's also very fun for rock climbing. So, and you can actually tell the sand is important. The sandstone aspect is because of the size. And if you've ever played in a sandbox or gone to the beach, you can feel that grit of sand. You can feel the individual sand grains in your fingers. And that is essentially what makes a sandstone a sandstone. And it also tells you that it is not the lowest energy environment, right? You do have to have a little bit of water to be able to move sand grains, but it's also not very high energy because we still have small things like sand grains. So that does make it really, really good for fossilization and preserving fossils.
Ooh, where can these rocks be found? We have a question from Cynthia.
Oh, where can these rocks be found? Yeah. Well, sandstones can be found a lot of places. I mean, classic places where you're going to see sedimentary rocks like that. I mean, I think of like the Utah national parks. Those are all classic sandstone deposits. Obviously, you can get sandstone outside of Utah. There, you can find sandstone in probably every single state. But be sure to look out for sandstone when you're hiking around, and anything that maybe was an ancient sand or river environment, there's a good chance that you're going to find sandstone there. But great question. I'll try to include some places where you can find it.
Nathan says sandstone is sand, but you can't make a sandcastle with it.
That's true. I guess you could make one if you wanted to carve it very slowly over time. So our second type of sedimentary rock is this one right here. This is called a mudstone. All right, so mud, instead of being made up of sand grains, is actually made up of clay and silt. So when you feel it in your fingers, it's more smooth and silky. You can't actually feel individual grains of mud in your hands like you can with sandstone. So it's a smaller grain size. Now that means it needed an even lower energy environment to be able to accumulate, or else if there was too much rushing water moving through it, it would all get rushed away. So if you find mudstone, you know that it was a pretty soft, slow moving environment, probably something like a swamp or a pond or a lake or something like that is a pretty common place where you might find mudstone. And again, because of its small grain size and its low energy environment, this is a great rock to find lots of cool fossils in. And if you want to find a fossil that's like a full skeleton, your best chances are going to be in a nice mellow environment preserved in mudstone. And mudstone, look at these mud cracks, how cool that is. Those formed millions of years ago, and we now have a snapshot into this past environment because of how this rock formed. Sometimes you might even find tracks of animals on these and traces of plants, and we can learn a ton about ancient environments because of mudstones. Okay. Mudstone is not so great for rock climbing. I don't recommend it. It's pretty dangerous. So this is another sedimentary rock called a conglomerate. So this is much larger grain sizes than either mudstone or sandstone. We have things in here that are like pebble size to small rocks, small cobbles, and it's eroding right in front of us. That's science in action. So this is a higher energy environment, right? Because to have enough energy to move around some of these big cobbles is going to take more energy than to move a grain of mud. So this means that yes, you can find fossils in conglomerates, but they're less likely to be found here. And if you do, they're probably going to be isolated pieces versus an entire skeleton. Also, conglomerates are not great for rock climbing because they fall apart so much. Our last sedimentary rock to discuss this today is this chunk right here. This is a chunk of limestone. So limestone is different than all the other rocks that we've talked about today because instead of being made up of sand or mud or some silica-rich sediment, it's actually made up of calcium carbonate, which is the same stuff that chalk is made out of that you might play with on the sidewalk. And chalk and calcium carbonate usually form from the shells and exoskeletons of teeny tiny marine invertebrates living in the ocean. So like an oyster or clams and coral and foraminifera, all of those critters have hard parts that are made up of calcium carbonate. And as they die, their skeletons and shells break down and land on the bottom of the ocean in layers, again, like we talked about with the depositional layers. And it actually, again, through enough burial and enough accumulation of those little itty bitty exoskeletons, it cements into a rock that we call limestone. Limestone is great for fossils. If you are interested in marine invertebrates, like ammonites and snails and oysters and all sorts of cool stuff, then limestone is going to be a good rock for you. If you're in Montana, you are surrounded by limestone. We've got limestone all over the place that preserves when Montana actually used to be an ancient ocean, which is also so wild to think about. So if you go to Lewis and Clark Caverns at all, then limestone is the rock that makes up those caverns, and all the hikes around there, those are all through limestone. And so you can see limestone throughout Montana and other places in the world, of course, too. Very, very common rock.
Ooh, which rock is the heaviest?
The rock is the heaviest. I can't lift them both up. Either, I think it's this one, but it might be, the andesite is pretty heavy too. Nope, it's definitely the amethyst. It's definitely the amethyst. Very fun question. Okay, we're moving on to our last and final rock type here, which is our metamorphic rocks. All right, so we started talking about the other two because now we're going to talk about what happens to igneous and sedimentary rocks as they go through a metamorphic stage. Now, metamorphic rocks form under intense heat and pressure below the Earth's surface. So that means both igneous and metamorphic rocks are happening mostly below the Earth's surface, and sedimentary rocks are happening at the Earth's surface. So we have a couple different types of metamorphic rocks. You have some that have gone through just a little bit of metamorphism, and then you've got some that have been very, very processed for millions of years under metamorphic conditions. So let's take a look at some of those examples. So we talked about, oh, I don't know where my slate is. That's okay. We talked about mudstone. And mudstone, when it goes through metamorphosis, it goes into a metamorphic rock. It actually goes into, oh, thank you, Angie. She's finding the rocks under my own nose. It turns into a rock that looks like this. This is called slate. So it's a very dark, very dense, heavy mineral or rock because it has been cooked underground and gone through extreme heat and pressure. So you can go from something like this to a low-grade metamorphic rock like slate, which is used in a lot of tiling in homes. So you might have some slate in your house. And then if you have slate that goes under more metamorphism, then it can eventually become a rock like this. This is called schist, and it is very shiny because we've got some very cool micaceous minerals that are cooking out under that intense heat and pressure, and actually forming layers of really shiny rocks in a form of foliation as the minerals change as they're being heated up and under so much pressure.
Mm-hmm. Ooh, you know what? There's a good question back here. Are crystals rocks?
Are crystals rocks? Well, I mean, technically, no. Though, I mean, you could like, yes, no. I don't know if there's necessarily, as a geologist, rocks are usually composed of many crystals and or minerals together to actually be something that you would study in petrology, which is the study of rocks specifically. And then mineralogy is actually the study of the individual minerals that are coming together to create those rocks. So we do, as in geology, differentiate between crystals and rocks. However, they're all being formed by natural earth processes, and they're all really, really cool inorganic structures. And if you call it a rock, I am not going to be bothered by that. They're very, very closely related and under the same umbrella. Good question. So back to metamorphic rocks. Let's see, earlier we had talked about this nice piece of granite. Oh, I just gave a hint about what I'm about to say. So this is granite, and over time, through metamorphic conditions, it can become a rock like this. And this rock is called a gneiss. That's right, it's gneiss. Now, it's not actually spelled how you think it might be spelled. It's spelled like this. So this is how it is. But it is a really fun word to play with, and you can go home and tell your folks that you got to see some nice rocks today. And here is a really nice rock. This gneiss actually came from Highlight Canyon here in Montana, outside of Bozeman. And gneiss is a pretty high-grade metamorphic rock. So it actually, it's higher grade because you can see these different color foliations in it, which is different than what we see in the layers of sedimentary rocks, which actually are preserving different deposition. These layers that you see are actually because of the chemical composition changing and delineating out as it is under intense heat and pressure. So it looks kind of like layers of sedimentary rocks, but we call these ones foliations, and they're what you find in metamorphic rocks. And you can find also, sometimes you can find really cool minerals in there too, like garnets and things like that.
Everyone says, wow, nice is nice. Those are nice rocks.
Nice, nice. Yeah,
Nice.
it is. It's very nice.
Yes.
And so then another example is going to be our sandstone. If you put sandstone into a metamorphic condition for a long enough amount of time, it's got a lot of, sandstone is made up of little quartz grains, essentially little kind of the same ingredients as glass. So if you put those under metamorphic conditions long enough, you actually get what we call a quartzite. And that's what this rock is here. It's very shiny and pretty. And you can kind of tell, like if you've ever seen a quartz crystal, it looks very similar to that, but just a little different because it's been cooked long enough in Earth's internal oven, if you will. And our last one to talk about is our limestone here. The limestone that we talked about, if you go through metamorphic conditions with limestone, you don't get a cheese cutter immediately, but you get marble, which is what this cheese cutter is made out of. This one's from my own house. And so marble is the metamorphic version of limestone. So it is really old, heated up and pressurized, ancient sea creature exoskeleton accumulation over time. How cool is that? How cool is that? I'm slicing cheese on really cool Earth history. So you might have something made of marble at your house, or you maybe have been to a museum or a historical place where you've seen marble statues. It's really popular to use because it's quite lovely and beautiful, and it's also easy to carve because it's made out of calcium carbonate, which tends to be a little bit softer than, say, a sandstone or a gneiss or something like that. So those are how some of those sedimentary and igneous rocks become metamorphic rocks. But how the heck does that actually happen? The processes that allow these rocks to change form are a lot of times a lot of heat and pressure and erosion. So water and wind breaking down the rocks into smaller pieces. Now, where we see this happening is a lot of times thanks to plate tectonics. So we here are all hanging out on Earth's crust. Earth's crust is made up of lots of different plates that we're riding around on and that are being moved around by the mantle underneath of our plates. And now as those plates move around, sometimes they run into each other. Like here in North America, two continental plates ran into each other back in the Cretaceous age of dinosaurs, and it caused these two continental plates to go upwards and form the Rocky Mountains that we've got behind us right now. And that causes a lot of intense heat and pressure, so that causes metamorphic rocks to form. It also causes enough pressure where the rocks are melting, creating igneous rocks, and then those mountains are exposed to wind and rain and water, and the sediments are slowly breaking down and going through river systems and being deposited. So it's really all interconnected. And that's also why we don't even have rocks from the earliest stages of Earth, because they've all been recycled already. We also see plate tectonics playing a role on the West Coast. So we have the Pacific plate going underneath the North American plate along California and Oregon, Washington, British Columbia, and Alaska. And then as that plate goes underneath, it gets really hot down there. It causes igneous rocks to form, metamorphic rocks to form, and mountains to form, which are eroding into our lakes and rivers and streams and being deposited as sedimentary rocks. And the cycle continues onward and onward in that general fashion. It can get a little more complicated than that. And if you're really interested in it, stick with the earth sciences in school, and you can take some fascinating classes in high school and college and grad school to learn even more about all the cool rocks and how much geology rocks. So thank you all for joining myself and Streamable Learning. Also encourage you guys to tune in with us again soon. We've got more awesome programs going on. I think next week we're talking about herbivore dinosaurs, so both of those. So you tune in if you want to hear about cool dinosaurs, and now you'll know a little bit about the rocks that they formed in. So
Mhm.
thank you, and hopefully we can have some questions.
Yeah, actually, there's a really good question that I've not really thought about, but Kevin wants to know, is glass a rock,
Mm.
and how do the rocks not burn up in a volcano? How do rocks not break underwater because of all the pressure? Ooh.
Those are fantastic questions. I mean, human-made glass is not a rock because we made it. Now, it will be interesting to see with the Anthropocene, and as we have littered lots of glass all over the planet, to see if that will break down and accumulate in its own sedimentary rock type, which will be fascinating. But glass does naturally form occasionally, usually in these volcanic settings. Though other things like chert, or they have agate, those sorts of things are also mostly, I mean, and they're not exactly glass, but they break a lot like glass, and they behave a lot like glass, and they have a lot of chemical similarities with glass. So glass is something that can be fairly naturally occurring. I've lost where we were with those
Lightning
other.
too. Lightning can strike and cause glass.
Yep, fulgurite.
Yeah. And rocks burning up in a volcano.
Rocks burning up in a volcano. Well,
Yeah.
some rocks are burned up in a volcano, and they're distributed usually as some sort of lava. Now, sometimes, I mean, there's just different grades of this. Sometimes the rocks are busted up so much that they're volcanic ash, right? And they're essentially now a sediment that is falling in the sky and is, again, just broken up bits of those volcanic rocks. So, I mean, yes, and volcanic rocks can then be just immediately melted again and turn into more volcanic rocks. It's the beauty of the rock cycle. Not only can they turn into each other, but they can just keep turning into themselves too.
Nice. Ooh, what's the hardest rock to find?
Hardest rock to find? Man, I have no clue, because I'm
Oh.
sure it's this really obscure random thing. There are a lot of rock types that are only known from very specific regions. Like, I mean, out here, people are, there's a lot, I mean, it's hard again because people are wanting to find like minerals. But if a hard rock to find is going to be one that's got something like rare earth elements in it, or gold in it, or platinum in it. Those are going to be really rare, hard rocks to find.
Here's a personal one. What's the coolest rock in your opinion?
The coolest rock, in my opinion.
What's your favorite rock?
Okay, there are these cool rocks that are like, I learned about in school, so stay in school, it's cool. But I learned about these really cool quartz monzonite rocks, which are essentially like very well sorted sandstone, or it's beautiful. It has to do with essentially really, really quickly moving river deposition being then going into more of a igneous situation. I don't know. I remember it being really cool, but that's out there. Really, my favorite rocks are any rocks that have fossils in them. So those are really my favorite rocks.
Those are my favorite too.
Yes.
Is gold a rock?
So gold is technically, well, an element actually at that point. Gold can be a component of a rock, but gold on its own is not technically a rock.
Yep. And then what is one of the easiest rocks to find?
Well, the easiest rocks to find, well, it depends on where you are. So when I was living in Oregon in the Willamette Valley, the easiest rock to find is basalt. So kind of like these ones, because of the Columbia River basalts that happened so long. And then, but here in Montana, it's probably going to be a metamorphic rock. If you're in Texas, it's going to be a limestone. If you're in
Florida here, so
Florida, it's probably going to be a limestone, or a sandstone, or something like that. So it really depends on what state you're in. So those are great questions, and stay curious.
Awesome. Well, we're going to share our screen with you one more time. That is all the time we have for today, but we encourage you to send us an email. If you've got questions that we didn't get the chance to answer, go ahead and send us an email to moroutreach@montana.edu. We've got it up there on the screen. As Amy said, next week we're going to be talking about herbivores during the Mesozoic, so some of these dinosaurs like you see above us. A big thank you to our partners at Streamable Learning. A big thank you to our paleontologist, Amy. From all of us here at Museum of the Rockies, thanks so much. Rock on. Have a great day.